Okay, so let's look at momentum conservation. What is momentum? Let's start with that one. So there was some answer over there. What is momentum? Mass times velocity. What if I say that it's not? You see, in your pre-reports, some of you were asking me how you can write formulas in your pre-reports. You see, most of the time we don't define quantities using equations because they might change. We define concepts based on ideas. So what is the idea behind the definition of momentum? So that, that idea will stay the same also in the relativistic case. But we will see that that idea doesn't necessarily give you m times v. Okay, that's the Newton's second law. That we will use. This will still hold if we can find the proper definition of momentum. This law will still hold. But again, this is just an equation. What is the momentum? So if you want to use this equation, you have to know what is the force, you have to know what is the momentum, etc. So it's not really the definition of momentum. It's the definition of the force more than the definition of momentum. So what is momentum?
I define it for myself as the urge or the power to stay or keep your velocity.
Okay, that's nice.
Or to keep your status of stopping.
Well, that's nice, but not very practical.
There is a change position with respect to time, particularly. Yes.
So you are still, you are basically reading this equation.
Before answering your question, could you define what's the meaning of momentum?
That's what I'm asking.
The definition of Turkish or English doesn't matter. Not in physics, because we don't know what's the momentum.
Well, that's what I'm asking. Really. I'm just asking the definition of momentum. How can we define momentum so that we will be sure that it will be valid whatever the laws of nature are? So that using that definition, depending on our understanding of the laws of nature, we can derive various expressions for momentum. And we will then see under which conditions this definition will hold.
Transferring energy.
What do you mean transfer of energy?
Like we have a particle and it has an energy. It moves one direction.
Okay.
And you calculate the effect and you see the difference between the energy.
Well, if you say that, I will then ask you what's the energy. So, it will go in a circle.
Resistance against change of velocity.
Well, that is what we call the inertia. Well, let me define it. Momentum is an additively conserved vector. This is how we can define it. It's an additively conserved vector in the sense that, what does it mean additively? So if you have various parts of your system, each one having a momento pi, p1, p2, p3, etc., then you can define the total momentum of the system as the sum of the momenta. We still didn't define what these momenta are, but at least we know one property of it. They are vectors. They should be vectors. Plus, if we have a complicated system, the total momentum of the system will be just the sum of the momenta of the parts of the system. This is one thing. The secondly, it should be a conserved quantity. This thing should not change in time if we have a closed system. If f is 0 for the whole system, it shouldn't change. Now, how do we define the P is equal to m times v as our momentum in Newtonian dynamics? Well, we have the 3 laws of Newton. If we have, let's say, 2 objects somewhat influencing each other, well, Newton's laws tells me that A should be equal to the acceleration of each one should be equal to Fi over mi. This is the expression of the Newton's law. The acceleration of an object is proportional to the forces acting on it, and the proportionality constant is 1 over the mass. So in the simple system, let's say that this is object 1, this is our object 2. The 2 exerts a force on 1. This is the force acting on 1 due to 2. And then the 1 will exert a force on 2. This is the force acting on 2 due to 1. This is Newton's first law. So it tells me that A1 will be, M1 times A1 will be equal to F1, F12, and M2 times A2 will be equal to F21. And Newton's third law tells me that F21 should be minus F12, which tells me that M1 times A1 plus M2 times A2, this should be 0, which will tell me that M1 times the V1 by dt plus M2 times the V2 by dt, this will be 0. But that same thing is d by dt m1 v1 plus m2 v2. This will be equal to 0. So this is, well, if you define the momentum of a point object as the mass times the velocity, this tells me that, okay, one thing, it is additive. Here I have 2 parts. The total momentum of the system will be the sum of the momenta of each one defined as mass times velocity, and this combination doesn't change in time. So this fits our definition of momentum. It's a vectorial quantity which is additively conserved. Because we can. It simplifies our computation. You see, conserved quantities in general are helpful. You see, using for example, using this conservation of momentum in 109, you could determine the velocity of the objects after 2 masses collide and stick together. You don't know what is going on there during that sticking process, during the collision process. Nevertheless, you can still determine the final velocity.
Is it the reason why momentum is more fundamental than velocity?
Well, we will come to that. Now let's look at the problem with this definition. When we have the Lorentz transformation, and when we look at the relativistic effects, it turns out that this quantity, mass times the velocity, is not something that is additively conserved. That will be the problem. To see why it is not conserved, it is not conserved in every reference frame. That's another thing we want. We want laws to be valid in every reference frame. You see, in this derivation, I didn't specify any reference frame. If you look at the Newton's laws, this law is valid in every reference frame. And the third law is again valid in every, let me make a small correction, every inertial reference frame. You just pick up one reference frame to study the problem. So in that reference frame, this is moving with some speed in that direction, this is moving with some other speed in that direction. In that reference frame, there are these forces. In that inertial reference frame, acceleration and the forces are related through this relationship, and there we have the action-reaction law. And then we arrive at our conserved quantity. In that, again, I repeat, in that reference frame. You see, this quantity need not be the same in every reference frame. So, for example, you might just go and start moving with a velocity v1. So in the reference frame fixed on you, this will be 0, v2 will be different, and this combination in that second reference frame will be different. This quantity is not frame independent. It depends on the reference frame. So if you calculate the momentum in a different reference frame, the momentum will have a different value. But still, if you stick to a single reference frame, no matter what happens in that reference frame, it will not change with time. So just keep these two concepts in your mind. One, we have conserved quantities, which means that they are not changing in time relative to a single fixed reference frame. Not a special one, you can just pick up any reference frame. But if you calculate the momentum, if you pick up your reference frame, calculate the total momentum of your system in that reference frame now, and calculate the total momentum of your system, I don't know, 1 hour from now, you will measure the same quantity. But if you go to a different reference frame, in that second reference frame, if you measure the momentum now, it will have a different value, a second value. If you measure it 1 hour after your first measurement in the second reference frame, it will still have that second value. So as long as you are fixed in that reference frame, you study your system using a given reference frame, it will not change in time. But if you go to a different reference frame, it will have a different value. So conserved, meaning it doesn't change in time. And invariant, meaning same for every reference frame. The number of students in this class. Well, that's an invariant. It's the same in every reference frame. But that is not conserved, in the sense that in 25 minutes, the number of students in this class will start changing in time. It's not conserved, but it is invariant. No matter what is my speed running through the classroom, I will count the same number of students in this classroom. But as I said, it's not an invariant quantity. It changes with time. You will be leaving, so the number of students will get smaller, and a new class will enter, so it will increase. So it will be just fluctuating during the day. Now, in defining the momentum, what we are looking for is a quantity. Well, that is not necessarily invariant, but it should be conserved in every reference frame. And there we also have a hint, at least for speeds close to the speed of, smaller than the speed of light, we can define the momentum as m times v. So I will be looking for a quantity which, if I assume the speed is much smaller than the speed of light, or similarly, I can just mathematically say that c goes to infinity, I should recover this expression. But when the c is finite or the speed is comparable to the speed of light, it might have a different expression. That's what I will be looking for. Of course, first of all, we have to make sure that there's actually a problem with this definition. So in one hand, there's the Newton's dynamics, which says that defines this momentum and says that this momentum is fine. So let's see if this momentum is fine if we do special relativity. Now, the typical example is just a two-dimensional collision. Let's look at these two objects, A and B. It's just like the colliding pucks that you have experimented with last semester. And let's assume that Well, in this reference frame, at least, momentum is conserved. And so what I will have is the A has initially some velocity in this direction. This is the A initial. B will have a velocity in that direction. This is the B initial. If you look at these two objects, the velocity of A, it will have an x component, which is minus the velocity of B, the x component of B. And if you look at the y components, velocity of A, y will be equal to minus the velocity of B, y. So there, yeah. I'm just creating such a hypothetical system. So initially they are moving in this direction, then they are colliding, and then they start moving in the opposite direction. Now let's go to our reference frame. Which has a velocity, which let's say, which has this velocity. So it's essentially moving in this direction. With and the velocity is nothing but the horizontal component of the velocity of the A particle. So in this new reference frame, the A particle will go down. And then after the collision, it will just go straight up. So A particle just goes down and up. The B particle now has a larger horizontal velocity. So the B particle will come here. Now here they collide, and it goes down. So in this new reference frame, now, in the initial reference frame, the collision was they just move towards each other, collide, and go in their own new directions. In this new reference frame, what happens is the mass A just goes straight down as mass B is approaching. They collide, and mass A just goes up, and mass B just changes its vertical velocity. Now, let's see if the momentum is conserved in the above reference frame, what happens over here? Let's calculate. Now, in this reference frame, I'm assuming A and B are to be identical objects. So if the momentum, we had defined the momentum as mass times the velocity, initially the velocities are just pointing in opposite directions, so the momentum, they are just pointing in opposite directions. After the collision, they are also pointing in opposite directions. So the total momentum of the system is 0 before the collision, and it is 0 after the collision. So momentum is conserved during the collision. Now let's see what this observer will see. Now what is, in this new reference frame, the x component of the velocity of A, the mass A. Let me put a prime over here. What is the x component? This is A, this is B. Yeah, it's 0. It doesn't have any horizontal component in this new reference frame. What about the y component? What is the y component of the velocity of A? Initially, let's say. Well, if you remember the addition of velocities, well, let's just derive it here. Delta y prime divided by delta t. T prime would be just delta y. The vertical lengths do not change. Delta t prime is just gamma delta t plus v over c squared delta x. So this is equal to, if we divide by delta t, this is vy divided by gamma 1 plus v over c squared times delta, not delta, but vx. Now let's apply it over here. Vay, well, initially in the other reference frame, it just has without the prime. This is Vay. Well, try to follow the primes. The primes are the quantities observed in this reference frames. Without the primes, it's the speeds observed in the other reference frame. Vay divided by, well, gamma, let me put a small index. It will be gamma v. Now let me just define this as v. The horizontal velocity of A is just v. Now I put a v over there because I will have many gamma factors corresponding to different speeds. So I just want to make sure that this is the gamma, which is defined as 1 over 1 minus this v squared over c squared under the square root, times 1 plus, well, what is this v? You see here, these are the quantities measured in the other reference frame. And this v is the velocity of the other reference frame. So we are here. The other reference frame is now moving with a velocity minus v, minus that v. So instead of that capital V, now this capital V, I will just put minus v. Because you see, if you remember our discussions on the Lorentz transformations, delta t is the time measured in a given in one reference frame. Delta x is the displacement in the same reference frame. And v is the velocity of that reference frame relative to whichever reference frame you are switching to. That was how we defined it. Now the initial reference frame is moving with a speed minus v relative to this reference frame. So that is why there I have a minus v over c squared. Well, vx, that is the horizontal component of the velocity of the A particle in that measured in that other reference frame, but that is just v. Now let's look at y. Now b, the velocities of the B particle. The velocity of the B particle, the horizontal velocity, will be, well, it's just, this is with the prime, this is vbx in the initial reference frame, minus v divided by 1 minus v squared over c squared. No, sorry, let me just call it 1 minus v times vb of x. Yeah, I'm just using the addition of speed. It's just the since this is the minus v, the speed of the other reference frame. The difference here, I also have a minus sign. Here the v is the relative speed of the reference frames. Here is the x component of the speed of the b, the velocity of the b in the other reference frame. So that's why I put a vbx. But keep in mind that that vbx is minus v. That is minus v. So that vby, now that v prime bx, this is minus 2v divided by 1 plus v squared over c squared. Well, it doesn't change during the collision. is the same before and after the collision, because in the initial reference frame, VBX is the same before and after the collision. Now let's look at VBY. Well, this is, in the primed reference frame, it is VBY divided by gamma V times 1 in minus V over C squared times VBX, which will be VBY divided by gamma V 1 plus V squared over C squared. And you see, the important thing will be this one, VA1 prime. This is, we had derived it before over there. VAY divided by gamma V 1 plus V squared over C squared. No, 1 minus. You see, in the initial reference frame, what we had this VAY and VBY, the y component of the velocities of these objects. They were just, when one is moving down, the other one is moving up. They had the opposite sign and the same magnitude. So the vertical momentum was 0 when we sum them up. Are you following? No, I mean, before it was 0. Well, after the collision, they had the same magnitude and moving in opposite directions. So the vertical component was, before the collision, it was 0. After the collision, it was 0. But now, their magnitudes are not the same in this new reference frame. So they don't sum up to 0. But during the collision, both of them change sign. Before the collision, if they are moving like this, after the collision, they are moving like in the opposite directions. So in the initial reference frame, this wasn't a problem because when we summed them up, they were 0. When both of the y components change sign, the total momentum, the y component of the momentum changed sign, but it was 0 before the collision. If you change the sign, it is still 0, but not anymore. You see here, M1, well, the masses are the same. MA is equal to MB, whatever the mass is. Let me just call it M. M times VAY, VAY prime, plus M times VBY prime, initially before the collision. This is equal to M times VAY divided by gamma V 1 minus V squared over C squared plus M times VBY, initial values, divided by gamma V 1 plus V squared over C squared. This is before the collision. After the collision, basically we have the same expression. Just instead of I, we have the final velocities. You see, now this is no longer 0 in this new reference frame. It was, this combination in the original reference frame was 0 because this and this, they were just opposites of each other. When we sum them up, it gave me 0. But now, these factors are different. So they don't sum up to give me 0. Well, it need not be 0, but if you look at this expression over here, in the this is in the initial, the y component in the initial reference frame after the collision. This is just minus that one. And this is just minus that one. because the y components during the collision, they just change sign. So this tells me that m times VAY prime plus m times VBY, the y component of the momentum after the collision, is not equal to the y component of the mass times the velocity, let's say, before the collision. So if we look at this combination, mass times the velocity, in both reference frame, well, we have one reference frame in which mass times the velocity is conserved, thinking that, okay, in Newtonian dynamics, we define this mass times the velocity as this additive vectorial quantity. But if it is conserved in one reference frame, it just turned out that it is not conserved in the other reference frame. So it basically tells us that m times v is not the correct form for the momentum of the object because it's not conserved. It doesn't fit into the definition. Now we have to look for a different definition. Now I will still expect some definition of momentum, which will be, let's say, some function. I don't know what that function is. It can be a function of the mass and the speed of the object itself. This v is the speed of the object itself, multiplied by the velocity. I will try to use this expression. And then I will try to guess what the form of f should be. I don't yet know it. But what I know is if this is the momentum, if this is the correct momentum of expression of momentum, then it should be conserved in every reference frame. That is the criteria I have. Well, I will just borrow from here. So I have to have, you see, another thing to note. If v changes sign, if this expression is correct, if the vector v changes its sign, the speed doesn't change, m doesn't change, so the momentum changes sign. If this is the correct expression for the momentum. But that means that since the velocities of the colliding object, the y components of the velocity, they just change sign. The y component of the total momentum should be 0 if it is to be conserved. Because I will be eventually saying that py is just f times m times v, the speed of a times the velocity of the a, the y component of the velocity of a, times f times m times vb times the velocity of the y component of the velocity of b. This is initially. Finally, after the collision, well, it's just the VAY and VBY, they change sign. They should be equal. But this already tells me that the vertical component of the momentum should be 0. Well, if that is the case, you see, this is the vertical component of the momentum before collision. Of course, instead of f, I have now this function of the m and va. Again, the function of m and vb this time. This should be 0. But keep in mind that VAY is just minus VBY. These are the velocities in the initial reference frame in which the momentum is already conserved. They are of opposite signs and equal magnitude, this VAY and this VBY. But that tells me that this function of VA divided by gamma V 1 minus V squared over C squared should be minus the same function, but this time evaluate that speed VB divided by gamma V 1 plus V squared over C squared. This should be 0. Well, let's cancel the gamma V's. So this tells me that FMVA divided by FMVB, this should be equal to 1 minus V squared over C squared divided by 1 plus V squared over C squared. Well, this is not the solution that I'm looking for yet. You see, on the left-hand side, I have an expression which might depend on m, but on the right-hand side, there is no m dependence. M dependence just cancels in this ratio. Secondly, on the left-hand side, I have the ratio of a function of VA only and the function of VB only, but on the right-hand side, I have a function of V only, of capital V. The first thing I need to do is I have to rewrite the right-hand side as a function of VA and VB. Again, that is something, well, it's a kind of a tedious algebra. Just go and calculate this combination, 1 minus VA squared over C squared. Well, let me make one correction over here. This is VA prime. Basically, since I'm evaluating that momentum in this new reference frame where the speeds are primed speeds. 1 VA prime squared divided by 1 minus VB prime squared divided by C squared. Now just go ahead and express these VA prime squared as the x component squared plus the y component squared. And then the x component, you know how it's related to the speed, the xy components in the original reference frame. The y component should be related in the original reference frame. Well, it's just some tedious algebra. If you do that all simplifications, you will see that this is equal to, let me see, 1 minus v squared over c squared. No, 1 plus v squared over c squared divided by 1 minus v squared over c squared, all of this thing squared. No. Exactly. They don't cancel. Just give me a couple of more minutes. We're here. Well, basically because I'm right here, I'm writing the momentum in my second reference frame. In my second reference frame, the momentum will be f times VAY prime plus f times VBY prime. No, these are not prime. This is prime only. This is only prime. Well, initial or final doesn't really make any difference because initially and final is just a sign change. 0, it's still 0. Okay, just keep a couple of more minutes. So it's just, just use the addition formulas to express these in terms of V. So you will just see this. If that is true, then this ratio is just 1 over square root of 1 minus VA squared over C squared divided by 1 over square root of 1 minus VB squared over C squared primed. So you see, now I have the separation of that expression as a ratio of something that depends only on VA prime and that depends only on VB prime. That tells me that Fm times V, whatever V is, whether, let's say V prime, should be equal to 1 over square root of 1 minus V prime squared over C squared, multiplied by some function of m. Because I'm looking at identical particles, when I take the ratio of expressions of this form, this alpha m, it just cancels, and I'm left with that ratio over there. Now I almost have an expression of the momentum of an object. This is just gamma. If you like V prime, the momentum in the second reference frame will be gamma V prime times alpha of m times V prime. Now what is left is what is alpha of m. But then we can cheat from Newton's dynamics. This should go to, if V over C goes to 0, at small speeds, this gamma, now V prime over C, gamma goes to 1, this becomes 1. Alpha m, nothing happens to it. This just becomes alpha m times V prime. But this should be equal to m times V prime, because we know from Newton's dynamics that is the definition of momentum. So this tells me that alpha m should be just m. Which kind of completes our proof. The momentum of an object should be m times v multiplied by gamma v. Well, if you like, just put the primes over there, but the prime reference frame is just an arbitrary reference frame. So if actually what we had shown is this one. The momentum in the second reference frame is equal to the mass of the object multiplied by the velocity measured in the second reference frame times the gamma factor corresponding to that speed. But the second reference frame is just an arbitrary reference frame, and everything over here just refers to our reference frame, which is just arbitrary. So this is true in every reference frame, not just that particular one. P should be equal to m times v times gamma. Well, on Thursday, we will also remove one assumption here. We made one assumption here. Well, that is one thing. We assume that V over C can go to 0. Are we sure that V over C can go to 0 for every particle? Light speed is the same in every reference frame. Here, basically, we are assuming that the mass is non-zero. Anyway, we will discuss that in more detail on Thursday.